So yesterday, we studied the free Klein-Gordon theory. That's the simplest quantum field theory we can study. It's a non-interacting scalar field theory. And today, we're going to add interactions and start to learn how to compute observable quantities in interacting field theories. So this process is going to take several lectures. And so what we're going to do today is derive the LSC reduction formula. So LSC stands for Lehmann, Szymanczyk, and Zimmermann. And what the LSC reduction formula lets us do is it relates scattering amplitudes, which are transition amplitudes from some initial state with some number of particles to some final state with some number of particles, to time-ordered products of fields. So at the end of yesterday's lecture, we computed the simplest time-ordered product of fields, the time-ordered product of two free fields. And so today we're going to relate scattering amplitudes and interacting field theories to time-ordered products of interacting fields. And then tomorrow, we will learn how to relate these time-ordered products of interacting fields to time-ordered products of free fields, and eventually back to the Feynman propagator that we computed at the end of yesterday's lecture. So that's where we're going. And so our basic object of study for now is write it in two different ways in the Schrödinger or Heisenberg picture. And so in the Schrödinger picture, we just want to compute the overlap of some initial state, t equals minus infinity, with some final state at t equals plus infinity. Or in the Heisenberg picture, we want to compute this quantity, where Fsi, where S is what's known as the S matrix. So the S matrix encodes all the information about how initial states can transition into final states. And in the free theory we studied yesterday, S is just the identity operator. There are no interesting transitions between different states in a free theory. That's basically what we mean by free theory, because there's no interactions. So it's often useful to separate out the non-trivial part of the S matrix. So we can write S as the identity plus IT, where T is what's known as the transfer matrix. And so really what we're interested in is the T matrix, where often we'll write the S matrix, but we're not really interested in this trivial part. And so transfer matrix, what do we know about it? Not very much at this point, but we do know one thing. It should vanish unless the total form momentum is conserved. We certainly don't want to allow transitions between initial states and final states if the initial state doesn't have the same form momentum as the final state. So just based on momentum conservation, we expect that the T matrix is proportional to a momentum-conserving delta function. And so it's conventional, again, to save some writing and reduce a clutter of our notation, is to pull out a momentum-conserving delta function and write t as this delta function times m. And what we'll mostly be computing is m, or more precisely, matrix elements, just particular transition elements. We can't compute m for all possible initial and final states. That's just too hard of a task. So what we'll really be interested in computing are f, m, I. And I'll often use the notation that this is equal to I, m of I to f. And so this is what's known as the matrix element. And this is what we will attempt to compute. We'll get partway there today and the rest of the way there tomorrow. OK. So that's what we're trying to compute. So which initial states and final states should we consider? So it's going to be useful. So let's first think about the free theory. So in the free theory, there's no interactions. But we can still set up initial states where we've got two particles that come in with some momentum and approach each other. So if we want to set up a state like that, we should use a wave packet. So in the free theory, we can define a wave packet by defining a creation operator I'll call A1 dagger. It's an integral of some function k where f1, for instance, could be some Gaussian that's centered around some momentum k1 and has some width. The precise form of the wave packet won't be essential. What we want is for A1 dagger acting on the vacuum to be localized around k equals k1 in momentum space, and x equals 0 at t equals 0 in position space. OK, so if we have a state like this, we can act with two operators like this and consider a state A1 dagger of t, A2 dagger of t, acting on the vacuum, where we want k1 not to be the same as k2. So what is this state going to look like? So here we've got a two-particle state. And these two particles have reasonably well-defined momentum. They're centered around the momentum of k1 and k2. In the far past, these are widely separated particles. And they come together and approach each other at the origin, near t equals 0. So they're not going to interact because this is a free theory. But this is the kind of state we'd like to consider. when we're considering scattering. So we have widely separated particles in the past. They approach each other, and then if we wanted to consider the future state that they would evolve into, well, there's no interactions here, but we'd also want to consider a state like this for F. So we have two widely separated particles in the future, for instance, and if we evolve backwards in time, they come together near the origin. Okay. So we're going to, so in the free theory, it's not too hard to construct states like this. What we're interested in, though, is not free theory, where there's no interactions, but interacting theories. So let's try to construct similar states in the interacting theory. Along the way, we're going to have to make several assumptions. The assumptions we'll make will allow us to derive the LHC reduction formula. These are going to be some non-trivial assumptions, though, and we'll arrive at the LHC reduction formula in the middle of lecture and spend quite a bit of time in the second half of lecture discussing under what circumstances these assumptions are valid. But for now, we're just going to make some rather bold assumptions. It will seem like, at least. OK. So let's go to the interacting theory. So we want to try to do the same thing. So the first thing that happens is the vacuum changes. And so I've been denoting the free vacuum as 0. I will denote the interacting vacuum as omega. And why is that? Well, in general, you expect if you change your Hamiltonian, the ground state will change. Generically, that will happen. So we'll just assume that there is, again, some Lorentz invariant state. That's the vacuum state in the interacting theory. We'll discuss more of the properties of this state tomorrow. But for now, all we need is that there is a Lorentz invariant vacuum that's the state with no particles. OK. Yeah, we'll discuss that more tomorrow. And so we're going to assume that A1 dagger at plus or minus infinity are still one particle states. Yeah. So this is somewhat weaker than we had before. Before, in the free theory, we had that A1 dagger created one particle state for all time. So we only really need that at plus and minus infinity, we have a one particle state. That's because in an interacting theory, particle number is not going to be conserved. So we'll have transitions between one particle states and multi-particle states. But we still, in the far past or far future, when all the particles are well separated, we want to have some sense in which we can talk about particle number. And so that's going to be this is a non-trivial assumption, and we'll come back to this in the later part of the lecture. OK. So with this assumption, we can write down some initial and final states for scattering. The simplest case of scattering is 2-to-2 scattering. So for the most part, I'll restrict to that, although our results in the end won't depend too much on the number of initial or final particles. So for 2-to-2 scattering, we can write down an initial state, which is just A1 dagger minus infinity, A2 dagger at minus infinity, omega, and a final state, which is A3 dagger at plus infinity, A4 dagger at plus infinity, omega. And so our goal is to compute f s minus 1 I. And the way we're going to do that is using the following identity, which I'll demonstrate in a minute. So we'll show that A1 at plus infinity minus A1 dagger at minus infinity is minus I. That's the integral of F1 integral. That's the integral of E I k dot x e squared plus m squared. Okay. So this will be key identity we'll use to relate the scattering amplitude to the time-ordered products fields. And so before we demonstrate why this is true, let's just look at this formula and see what it means. So first of all, here we've got the Klein-Gordon operator acting on the field. So this would be 0 in a free theory, but it's non-zero in general if we have interactions. So this is just saying, so in the free theory, the right-hand side is just 0, and A1 dagger at plus infinity and minus infinity are the same. But it's non-zero in general. And the assumption we will need to make in order to derive this is that even in the interacting theory, AK dagger of t is minus I integral d3 x e to the minus ikx d0 5x plus I ek 5x. So this is one result you demonstrated in tutorial yesterday. So we're assuming that the relationship between the creation and annihilation operators and the field operators is the same in the interacting theory as in the free theory. And what's going to change is not the relationship between the two operators, but instead the time dependence of the two operators. So that's another assumption we're making. So given those assumptions, let's demonstrate this identity in the middle of the board up there. So first thing we can do is we can write a1 dagger of plus infinity minus a1 dagger minus infinity as a time integral of a total derivative okay. So this is just an integral we can do. Then we can plug in the result from tutorial yesterday for creation operators and our definition of a1 dagger of t. So a1 dagger of t gives us a integral d3k f1 k. And then we have ak of t. We also have this time integral, which we can combine with the spatial integral in this equation for ak dagger to give us space-time integral. And we've got d0 of e to the I k dot x d0 5x plus I ek 5x. Okay, and so we're not going to deal with this integral d3k f1 of k. That's just going to stay the same, so let's just look at this part. This integral is already in our useful identity. We can just leave that alone. So this part is equal to the integral d4x. If we just do the derivatives, we get e to the minus I. This should have been a minus. Ik dot x. But, yeah, that's correct there. And we'll get 4 terms from doing this derivative. So one term we'll get is if we act with the time derivative on d0 5x. We'll get another term if we act with the time derivative on here and multiply it by this I second term. And that gives us a plus ek squared 5x. And then we have 2 other terms. If we act with the time derivative on here and multiply by this term, we'll get a minus IEK times d0. And we'll get exactly the opposite thing if we act with the time derivative on here. So those other 2 terms will cancel. OK. It's starting to look like our useful identity. We can write, so ek, remember, is k squared plus m squared. So we can write this as d0 squared minus gradient squared plus m squared 5x. So this is acting on by 0, but if we integrate it by parts twice, we can move this gradient onto here, and then we just get the k squared plus k squared that we wanted to go back to this line. And so this is precisely what we wanted. We just combine the derivatives into the Lorentz invariant combination of derivatives, we get d squared plus m squared 5x. All right. And we get we can do the same thing for the annihilation operators just by taking the conjugate. So that will just change the signs of the i's.
Excuse me.
Yes.
Can you please explain me how did you get the factor of d squared in the second line?
In the second line.
Yes.
Yes. So this came from acting with a time derivative on the exponential. So that brings down a factor of minus I ek. And we multiply the derivative of this term by this term, we get this term. There are two terms I didn't write, the derivative of this term times this term, and this term times the derivative of that term. Those terms cancel.
I was wondering why we are using the measure for momentum, which is not Lorentz invariant.
Well, so we wanted to create a wave packet that was localized in both momentum space and position space. And if we so we integrated over the energy too, then then we would have trouble imposing this condition. So we want to our particles in our initial state and our final state are on shell, meaning that they satisfy this equation. If we impose this equation, we've already determined the energy of the particles. So we can't integrate over that as well. OK. And so similarly, for A1 of plus infinity minus A1 of minus infinity, just with I goes to minus I on the right-hand side. OK. So now that we have this identity, we can compute scattering amplitude. So this is equal to omega A4 plus infinity, A3 plus infinity, A1 minus infinity, dagger, A2 dagger of minus infinity, omega. And so one thing we notice about this expression is that the creation and annihilation operators are already time ordered. So we can just throw in a time ordering symbol here. So again, time ordering symbol means put the latest operators to the left. OK. And now we can use the identities we derived. And to save some writing, let me introduce shorthand notation for the right-hand side, this identity. We'll say that this thing, the right-hand side, is defined to be, call this I1 dagger. Just a name for that integral. And so then we'll use the identities. So use A1 dagger of minus infinity, A1 dagger of plus infinity, plus I1 dagger, and for the annihilation operators, I'll call, again, the integral that we just derived, I4, without a dagger. OK, so we can then plug our result in, and we get that Fs minus 1 I is omega t of A4 minus infinity, A3 minus infinity, A1 dagger of plus infinity, A2 dagger of plus infinity, omega. You get a whole bunch of terms that involve both the creation or annihilation operators and these integrals, which I won't write out. I'll explain why in a minute. And then we also get the term that only contains these integrals.
Should that I1 dagger have a minus?
A minus? Let's see. I defined it. Yes, that's right. Okay. Okay, so let's look at what we have here. So because of the time ordering symbol, this term is equal to, well, we should order all the operators so that A1 and A2 dagger are to the left, because these are at later times. A3 and A4 should go to the right, start earlier times. And but A1 dagger is a creation operator, so it annihilates the bra vacuum, and the annihilation operators annihilate the ket vacuum. So this term is just 0. And similarly, because all of the creation operators are at plus infinity and all of the annihilation operators are at minus infinity, all of these terms that contain at least one creation operator or at least one annihilation operator are 0, because all of the annihilation operators are brought to the right, where they annihilate the vacuum, and all of the creation operators are brought to the left, where they annihilate the vacuum. So,
could you repeat again why the first term is 0?
Yes, that's because this first term, due to the time ordering, this term is equal to omega A1 dagger of plus infinity, A2 dagger of plus infinity, A4 of minus infinity, A3 of minus infinity. And we're still assuming that the annihilation operators annihilate the vacuum. So that means the creation operators annihilate the vacuum from the right. So So this term is 0 due to the time ordering and the presence of creation and annihilation operators. And we had 4 creation and annihilation operators here, but we just needed 1. So for time ordering, then because these are at plus or minus infinity, they'll always be the rightmost or the leftmost operators. So the same logic implies that all of these terms are also 0.
I'm sorry, this might be pretty annoying, but when we change that to a minus in the second expression so when we say a1 dagger of minus infinity is a1 dagger of plus infinity plus a1 dagger,
Yes.
should you change it to minus in the second line as well?
I'll have this. This is going to be a definition. I don't want to carry around minus signs. So this, just think of this as a name. Don't think the dagger as being the conjugate. So these are just names of integrals. The formula are going to be long enough without extra minus signs.
Sorry.
Okay. So we're almost there. So we can now take the wave packets were useful in this derivation. They no longer play an important role, so we can take f to be extremely peaked around k1, so that it just becomes a delta function. And in this case, our expressions for I1 dagger and I4 are simplified. So I1 dagger then just becomes plus I integral d4 x1 e to the minus I k1 dot x1 e1 squared plus m squared of phi of x1. And so here, what I mean by d1 squared is eta d nu d dx1 nu d dx1 nu. It's just a shorthand notation. And I4 is the same thing with just a minus I and a plus I. Okay, so we've taken this limit. We have arrived at the LSC reduction formula. Let me go to a new board. So putting together our results, we get So we have an integral for over space for each of the particles. And then we have a Klein-Gordon operator for each of the particles. And finally, we're left with a time-ordered product of the fields, as promised. And so I've introduced some notation so I could fit this on one line. So here, phi 1 is defined to be phi of x1. I'm already defined dj squared, and I've also introduced the notation that lambda j is -1 for final states and +1 for initial states. Okay, I've written it in a way so that it's clear what to do if we're interested in n to m scattering instead of 2 to 2 scatter. So we just have more integrals, more Klein-Gordon operators, and more fields in our time-ordered product. So this is a key result. So this is one of the key steps that will let us compute scattering amplitudes in interacting field theories. So we've a bunch of integrals and derivatives to do, but we've made some progress. So we've reduced the scattering amplitude to a time-ordered product of fields. Yes.
Can you justify again why it's okay to just put in a time ordering symbol just because they happen to be time ordered at the start?
Well, so the time ordering symbol just means take the operators that are to the right of them and put them in time order, the latest to the left.
Yeah.
So it doesn't change the expression.
Well, it doesn't change it at the start, but then once you start replacing them with other things, it will change the expression.
Well, it doesn't. These are identical. These two lines are the same, mean the same thing. This, it certainly simplified our derivation later, but that's a benefit to us.
So it's okay even when you're replacing like A4 plus infinity with A1 of minus infinity. It's still okay to say, like it's still okay.
That's right.
Put in the time ordering?
If we didn't put in the time ordering, we tried to do this derivation. We'd still do the same thing. These terms wouldn't all be individually 0, but the equation would still be true, so they'd have to somehow cancel between themselves. That would, it's not at all obvious to me how that happened, but these two lines are identically the same. So it must be the case that there's just some cancellation otherwise. Well, then we wouldn't have the time ordering here. So it doesn't have to be a cancellation, but this expression would also change. So we'd have a whole bunch of things that would cancel off the commutators we need to put this in.
It seems like replacing x with x squared when x is 1, and it's true there, but it won't be true if we change x in general.
X? Where's X?
Sorry, no, I'm just trying to make an analogy. It's true in that case, that's the time ordering symbol, but that is true in that case, that it's in the time ordered product or whatever it's called, but general. And it's money.
Yeah. So the final line would have a whole bunch of terms, and there'd be no time running here. So this expression would also change. Then we could use, I guess, the commutator to put this in the time ordering order, and the extra terms we get from the using the commutation relation should cancel off these terms. So that would be a much more difficult route to arrive at the same result. Okay. Yeah. So this is one of our most important formula in this class. So we'll see how to use it and compute these time ordered products tomorrow. But I want to spend the remainder of today's class going back and re-examining some of the assumptions we needed to make in order to derive this.
Can the reduction formula be generalized to n particles, or are there fine points to be set?
It can be generalized to n to m scattering. What would change is, we would just change the number of terms in this product. So this would just change to n plus m. Here in this I, this would just change to n plus m. And over here, we would have n plus m particles in the, or n plus m fields in the time ordered product. Yes.
I'm not really sure how to phrase this exactly, but when you took f1 of k to the delta function, and then you changed k to k1, but then you also changed x to x1, but x is just an integration variable. So at the end of the day, like when you integrate over it, it's just like it doesn't.
Yes.
So what's the distinction between like phi of x1 and phi of x2 and phi of x3 in the final reduction formula? If x is not.
So up until this point, and up until we put things together, we were just considering one particle at a time, and we were integrating, as you said, we were just integrating over some dummy integration variable. But once we multiply together, say I1 and I2, we should be doing two integrals over two different dummy integration variables. And so I just gave them different names to keep them separate. But in this formula, I could have written nothing would change if I added a subscript 1 to all of the x's.
Then at the end,
Yeah, just isn't that just phi of x to the power of 4?
Well, so we're integrating over x1, x2, x3, and x4 and x4.
But is that in the integral?
Integrating over them all separately. Yes.
Okay.
So we're doing an integral over the position at which we're evaluating the field operators.
So those brackets around the integral,
Yeah, should really end.
Yeah, that's fine.
Yeah, and here.
Oh, okay.
wait, but is that in the integral or not?
Oh, sorry. The product, we're making the product over this part, and the integral is over, then we're integrating over everything. Everything is an integral. Everything to the right of here is inside the integrals. So in this case, we're doing 4 integrals. We've got 4 exponential factors, 4 Klein-Gordon operators, and the time-ordered product of 4 fields. Yes.
Sorry, and just to clarify, that kj and xj, they are 3 vectors, right?
No, they're 4 vectors. 4 vectors. We've got a D4 x here, and this is the 4-dimensional dot product of k and x. Okay. So let's check our assumptions. Or examine them, at least. So our main assumption was that A1 created a one particle state. And because we assume that the relationship between the creation and annihilation operators is the same in the free theory and the interacting theory, this means that we also are assuming that phi of x acting on the vacuum is also one particle state. So we assumed these are one particle states. This is not obvious that this is the case, so let's check whether this makes sense to make this assumption. So one property we'd like one particle states to have is that the overlap between the one particle state and a vacuum state, which we'd like to interpret as having no particles, should be 0. So we want the one particle states to be different from the vacuum state. So let's compute it, or try to compute it. We haven't assumed much about our theory, but let's just look at the expression for the overlap of the vacuum state with one of these one particle states. See what we can say about it. So is this 0 or not? So what can we do with this? We haven't specified our theory, so there's not a lot. One thing we can do is we can rewrite phi of x as e to the I p dot x, phi is 0, times e to the minus I p dot x omega, where here these p's are the momentum operators. So this is just the translation operator. We've applied the translation operator to space-time translation operator to phi of 0 to get phi of x. It's basically a generalization of what the relativistic generalization of what we do when we go from the Heisenberg to the Schrodinger picture. So that would just be, you just take the 0th component of that, and that'd be going from the Heisenberg to the Schrodinger picture. So the relativistic generalization is just, we call that the space-time translation operator, and this relates phi of x to phi of 0, like this. But if we want to assume the vacuum is translation invariant, then we apply the translation operator to the vacuum, we should get back the vacuum. So this is for this. Translation invariance. And is there any reason to expect this to be 0? No. In the general theory, this will not be 0. And there will be overlap. Phi can get an expectation value, and we can interpret that as being an overlap between one particle state and phi. To put this interpretation on the state phi omega. So there's no reason to expect this to be 0. And, well, we assumed these are one particle states in deriving the LSE reduction formula, and I just told you that that's one of our key formula for computing scattering amplitudes. So there must be some way to save it, and fortunately we can. So in general, this is just going to be equal to some number, v. And if we redefine our field by shifting the field by this constant v, then we can save things. So this implies then that omega by tilde of x, omega is 0. And so in order to use the LC reduction formula, we're going to have to shift our field so that we can put this interpretation on this state. And I'm going to drop, for notational simplicity, I'll drop the tilde in what follows. All right, so there's one property we'd like.
And how legit is to do that? And to shift my field whenever I have this kind of problems. What is physical meaning?
Well,
I mean,
so
the fact that the V is still there is that when I apply my field operator to vacuum, there's still some part of the vacuum there, right?
that's right.
And what? So
Well, so we're saying what I'm saying is that phi tilde is a better choice of operator than phi.
just because you're interested in seeing
Seeing
how
how it, well, in particular, if we want to use this formula in the way I've described it, then phi is a bad choice, a field operator, and phi tilde is a better choice.
So phi here is a free field.
Phi is an interacting field.
The interact.
Interacting field.
So we're shifting the interacting field
That's right.
to get some other interaction.
So, right.
Or to get some.
So in some sense, our choice of field is like a choice of coordinates. We can, there are field redefinitions we can do that don't change the physics. So here we're doing a field redefinition so that the physical interpretation of what we're doing makes sense.
But this shift, you change the Lagrangian of the theory. So for example, if you write the phi to the 3 theory, the Lagrangian is not like phi. Again, phi tilde to the 3 plus some concept.
That's right. That's right. If we change the field, we're going to change the Lagrangian, and that's a very good point, and I'll come back to that.
The physics will change.
The physics won't change. The Lagrangian will change, but the physics.
and there's a term of the Lagrangian in the energy momentum tensor, right? With the delta and L.
Yes.
So I mean, we will see that there, but maybe not.
Yeah. Well, let me come back to this point near the end of the lecture, how the Lagrangian changes. Okay. So So we've looked at the overlap between the, we'd like to consider our one particle states and the vacuum state. That's not all we mean when we say that a state is a one particle state. We also need to look at the normalization of those states and their overlap with the multi-particle states. So let's look at the normalization first. So what's the overlap of So in tutorial yesterday, you computed the form factor. So that's this quantity here. And what you found was that this is just e to the ikx. And so that result had to do with the normalization of our fields and the relationship between the field and it's the creation and annihilation operators. And we're assuming that that relationship is unchanged. So that was another assumption we made. So let's see if we get the same result as you did in tutorial for the free fields, e to the ikx. Again, there's not a lot we can do with this expression without specifying the theory. But we can, as before, write phi in terms of translation operator. And so K here is a momentum eigenstate. So it's an eigenstate of the operator e to the IPX. Should put hats on here. So this is e to the ikx, which is what we want. But we're also left over with this extra factor, which we want to be 1. So that the normalization of our field is correct.
How do you plot the e to the ikx?
So this is, we're assuming that, again, that this is a momentum eigenstate.
But it's the
And-
momentum now.
So we're labeling it through momentum, and we're assuming that the 0th component is equal to square root of k squared plus m squared. And so that's what I do.
Oh, and the other one is the invariant.
Yeah, so this is invariant. Okay, so we want this to be 1 so that our one particle states are correctly normalized. Again, we have absolutely no reason to expect this to be 1. And in general, it won't be. Which, again, we can fix just by redefining our field. So we can fix this by rescaling. Where n is just some constant. And again, drop the tilde from here out. Okay, so if we shift and rescale, we can make the relationship between the creation and annihilation operators and the field operators the same as they were in the free theory. We can make the overlap between one particle state and the vacuum 0. But we also would like to be able to distinguish one particle states from multi-particle states. So that's the last thing we need to check, is that what I've been calling one particle states are actually different from the multi-particle states. Okay, so for now, let's assume that there are no bound states. If we have bound states, it will complicate our analysis. So let's just assume that there are no bound states. And what I mean by there are no bound states, well, yeah, that should be clear. So that the well, let me explain a little bit. So if there are no bound states, we expect the lowest energy states are the vacuum states, then the one particle states, and then there will be the multi-particle states will have a greater energy.
Sorry, so what's the bound state?
So a bound state would be, for instance, if we have, say, an electron and a positron, we could compute assume they're at rest relative to each other and extremely far away, then the energy of that state would just be the sum of the masses of the two particles. But if we bring them together, there's an interaction between them that reduces the energy. So if they're at rest close together, the energy is less than if they're well separated. So there's a that's what we would call a bound state. Is if they're that's what I mean by bound state. Is that any interaction energies. If there's a bound state, then there's a negative interaction energy between the particles. And so if there are no bound states, we're assuming that there's no interaction energy or it's positive. Okay. And yeah,
That means no bound states in the free or the interacting?
in the interacting pair. So we're dealing with an interacting pair. So yeah, there are many interesting interacting theories that do have bound states, but for simplicity, we'll just exclude those for now. Okay, so what we want or at least the first thing we might try to think we want is that the overlap between our one particle state and a multi-particle state is 0. And so here I'm labeling the multi-particle state by the total 3 momentum. And in general, multi-particle state will have some other parameters we need to specify it. Maybe it might be some discrete parameters and some continuous parameters. And I'm just lumping those all together by sigma. So this is all other parameters we need to describe the state. OK. And as before, there's not a lot we can do with this without specifying the theory. So as you might guess, what we can do is use the translation operator. And And there's no reason to expect this to be 0. And it's not so simple as before, because here there's many different states, and it's not at all clear what we can do to, we can't just do something as simple as shifting it to set all of these amplitudes to 0. So let's just give this a name. This amplitude, let's call it A sigma of P. And it's, in general, not 0. OK, so this seems to be problematic. This seems to be telling us that we can't distinguish one-particle states from multi-particle states. But we've imposed slightly too strong of a condition here. So we can relax this a little bit. So after all, we want to be able to describe things like particle decay, where a particle, say, could decay into several particles. So there might be a transition from a one-particle state initially to some multi-particle state. But what we really want is just to be able to distinguish one-particle states from multi-particle states in the far past and far future. And so maybe a better thing to ask is whether this amplitude is 0. This is a one-particle state in the far past or far future. Turns out this is a little bit too strong as well. All we really need is because these momentum eigenstates are not normalizable, what we really just need is the normalizable multi-particle states to have no overlap with our one-particle states in the far past or far future. So here, this is a normalizable state. Multi-particle state. And so can write psi then as a sum/integral over sigma, integral over p of some wave packets, multi-particle wave packets. And so this sum/integral, remember, sigma was just all of the parameters, other parameters we needed to specify the multi-particle state. Some will be discrete, some will be continuous. OK. So let's compute this overlap, and we better hope it's 0.
Sorry, can you just reiterate what you mean by the difference between the P sigma state and psi, which you call a normalizable multi-particle state?
Oh,
Sorry, I know you said it quickly.
so these states P sigma are momentum eigenstates. So they're not normalizable. Remember, so if we compute, say, the norm of a one-particle state, we'll get a delta function.
Yeah.
And the free theory, the same thing will happen here. So we just want to consider normalizable states. OK, so this overlap is what we want to be 0. So So these are what we want. Okay, so let's try to compute this. And now we've got a little more to work with. So psi, A1 dagger, omega. If we just plug in our definitions of psi and A1 dagger, we get minus I times the integral of psi star, integral d3k, f1 of k, integral d3x. And if we use, so A1 dagger involves AK dagger, and if we use, just write that in terms of the field operators, we get this expression. And so this is what we computed before. This is what we called A sigma of P times e to the I P dot x. And to avoid writing the whole line again, let's just write the part in the square brackets. So we can write the part in the square brackets after we do the time derivatives here as I P naught plus K naught e to the I P minus K x, A sigma of P. And so we can then, in this line, do the x integral. The x integral is just going to give us a delta function setting p equal to k, three-dimensional delta function. Use integral d3x to the I k minus p dot x is 2 pi cubed delta 3 k minus p. And that will let us do the k integral. And then what we get is psi A1 dagger omega is some integral T3 P 2 pi cubed. We have a P naught plus K naught from here. Okay, so that's what we've got. And what can we say about this integral? So here's where our assumption that there are no bound states comes into play. So we have that P naught is p squared plus m squared, so 1/2, where m is the invariant mass of the n-particle state, of the multi-particle state. And k naught is p squared, not k squared. We've already done the k integral. There's no k left. It's m squared to the 1/2. So the fact that there are no bound states means that m, the invariant mass of the multiparticle state, has to be at least as big as the lowest possible invariant mass of the two-particle state, which is greater than the invariant mass of the mass of our one-particle state. So P naught is strictly greater than K naught. And that tells us that this integral here is going to oscillate more and more rapidly as t goes to plus or minus infinity. And so regardless of what's happening with these functions here, the fact that this is oscillating so rapidly means that the contributions will, from different neighboring regions, will just cancel out. It's actually general property of integrals of this form that they vanish as t goes to infinity. It's a consequence of what's known as the Riemann-Lebesgue lemma. So the fact that P naught is greater than K naught means that oscillation will increase, and the P integral will vanish. As t goes to plus minus infinity. So, as we needed, we have that psi A1 dagger plus or minus infinity omega is 0. And so the one particle wave packets, one particle states at plus and minus infinity have no overlap with the multi-particle states. And physically, this is just because one particle wave packets and multi-particle wave packets spread out differently as t goes to infinity and or plus or minus infinity, and the overlap goes to 0 in the limit.
Wouldn't that happen for any relation? I mean, if they are different, P0 and K0, like it's an oscillating thing. Why do we need that P0 degree?
Well, if P0 is equal to K0, that would be a problem.
If it's equal, but if they're just different?
Different, that would be fine, yeah.
Ah, okay, so.
But, yeah. So, yeah, if we had any multi-particle state that had the same invariant mass as the one particle state, that would be a problem.
So the problem would be if there was a bound state with big N equal to N.
Yes. Okay. So in the last few minutes, I just want to come back to summarize and come back to your questions about what happens to the Lagrangian. So this, so what have we done today? So we've derived the LC reduction formula we had to make some assumptions to derive this formula that relates the scattering amplitudes to the time-ordered products of interacting fields. And those assumptions were related to what is a one-particle state in the interacting theory. So we just spent the second half of lecture showing that we could make our interacting fields satisfy the assumptions we needed to make to interpret, to write down one-particle states in the interacting theory. And we saw that in order to do that, we needed to shift and rescale the field. So that means that we start, we're interested in studying some interacting field theory. Say we start with our Klein-Gordon theory. And add an interaction term, say a phi cubed interaction. In general, we can't use the LSE formula, and we're not going to be able to study scattering using the theory we're interested in. What we have to do is shift and rescale. And if we do that, we're going to change our coefficients. Not only change our coefficients, but we'll get a new term. From shifting this, we'll generate a linear term. And so we can write so even if we're interested in this theory, this is the theory we have to study in order to use the LSE formula as I presented it here. So we change our coefficients, generate a new interaction. And these, this is required in order to use the LSE formula as presented here. So in other words, we're required to renormalize our theory. And so we'll study renormalization in much more detail in QFD2. I'll come back to it a little bit in my final lecture before Tibor takes over. But it's extremely important to point out that this is not something there's no point out that just we're forced to do this in order to proceed to develop the formalism of perturbation theory that I'm going to tell you about over the next few lectures. This is not a choice. We're forced to do this. This comes in basically just if we think carefully about what we're doing when we're doing perturbation theory, we're forced to renormalize. So for most of this course, we're going to ignore this issue. And so for now, we will assume omega 5x, omega is 0. The form factor is e to the ikx, just like in free theory. But we'll assume this is also true in interacting theory. And we're also going to make the assumption that all of the z's are 1 and all of the y's are 0. This is OK to do at leading order in perturbation theory, which is what we will, well, that's the first thing we should study, is the leading order in perturbation theory. It's generally not an OK thing to do beyond leading order. So we'll make these assumptions for now. Sometimes I'll briefly mention beyond leading order, but it's not a consistent thing to impose both of these conditions beyond leading order in perturbation theory. And usually these are the ones we want to impose. So as we'll see in my final lecture and more in QFT2, we'll have to violate these assumptions. And there are particular choices of Z and Y we'll have to make. But we'll come back to that later.
There is Y as a function of Y, or it's just a number?
It's just,
Good. I understand that if we shift, if we rescale the field, it's a number. We
Yes.
have here. And if we shift it, like the derivatives, if we shift it by a constant number, the derivatives equal matter in
Right.
the square and third term. I would get like functions.
the way I've presented things here, you just think of these as numbers for now.
Okay.
That's an issue we'll come back to, what exactly these mean, and in the 1 minute, or negative 1 minute, I don't have time to go into that. So. Okay, so that's the LSE reduction formula. So we've gone partway from computing scattering amplitudes, and tomorrow we'll learn how to compute this term. So that's where we'll go tomorrow. Any other questions? Yes.
In considering the invariance of the direction vacuum, we just considered the translation invariant. What
Yes.
about rotation?
It should also be rotationally invariant, yes.
But not boost
Boost?
or
Yes, we
also
boost, so we assume it's Poincare invariant, usually.
the vacuum.
The vacuum is Poincare invariant. Any other questions? All right, I'll see you this afternoon.